you can assume that there's an average value of the superficial velocity of the gas going through. You can determine that. And the power per unit mass is not that easy to measure because we don't, actually it's not usually monitored on small fermenters because it's so small, the amount of energy that's used is small. So there's not usually, what are those things called, torque, some kind of, they monitor the torque in the motor. But, so we don't have this set up, we don't have our bioreactor set up to do this. You can measure the KLA though, using an online method, and I can show you how to do that. Okay, so point 1 is experimentally determined, and it should be determined for each culture problem. Okay, so let's talk about the oxygen supply to the bioreactor. We're going to flow in air, and it's going to be compressed air, obviously, or it would move. And we don't really pay attention much. We have a little flow meter that we can see. We actually have a mass flow controller in the bioreactor, so it determines exactly how much flow of gas there is. Normally, in E. coli fermentations, you're not going to exceed about 1 volume per minute. Okay, what is volume per volume? If you've got a 1 liter of liquid, then it would be 1 liter of gas per minute. That would be 1 ddm. Okay. So we can see on a little flow meter that the gas is turned on, and there's a little sparger in the bottom of the bioreactor, and you see the bubbles coming out. And then we have a dissolved oxygen probe, and we can monitor that. We don't have a dissolved oxygen controller, as I've already said. So we will adjust that manually, and that'll be just fine. Okay. I think I've already talked about this. Yeah. Okay. Again, this is we can affect the flow of gas by increasing the stir speed of the motor, and that's easy to adjust. Okay. So here it is. We can stir faster. This is our motor, and there's our power per unit mass, and that's how we do that. We can increase the oxygen supply. We're really not going to talk about that because we don't do that in our process. Okay, but it's important to know that we can not only increase the stir speed, we can also increase the airflow rate. Like I said, 1 ppm is kind of an expected flow rate of the oxygen. But we cannot, there's going to be a maximum possible stir rate on the bioreactor. The motor will only spin so fast. I think it's like 1,000 RPM. And the airflow rate cannot be increased indefinitely because what happens is that you flood the impellers. And I know I explained this in the 160B class, but basically what happens is you're flowing so much air in there that a pocket of air forms around the impellers, and so they begin to stir very fast, and they're not stirring liquid, they're stirring air. You get no bang for your buck in that case, and this is called flooding. So when flooding occurs, there's a notable drop in the power being fed to the mixer because it's no longer stirring liquid, it's stirring air. So the demand for power on the motor goes down. Okay, so let's talk now about pH. So just a reminder, we all remember that water dissociates into hydrogen and hydroxide ions, and the product, the product, okay, there's 10 to the minus 7 hydroxide ions are produced when you dissociate. You can dissociate the water such that you get 10 to the minus 7 hydroxide ions, and you will also have 10 to the minus 7 hydrogen ions. So the product of these two is going to be 10 to the minus 14. So our pH is on a scale of 1 to 14. Okay. And so the concentration of hydrogen ions will be increased when compounds are added which release the hydrogen ions, such as an acid. Okay. So sulfuric acid is going to dissociate in the liquid to 2H plus and SO4, and then that's going to cause you to have an acidic value pH, or the pH is going to be low. Okay, so you can calculate the concentration of hydrogen ions from the pH, so you all remember how to do this. The concentration of hydrogen ions is going to be 10 to the minus pH value of the system. Okay, so if it's 7, if it's exactly 7.0, okay, that's exactly neutral, right? So this would be the concentration of hydrogen ions. And if we take a look here, what is the value at 10 to the minus 7 or 10 to the minus 7.2? Okay, this is the difference in the actual concentration of hydrogen ions. So it's important to know that increasing the pH by 0.2 only, 0.2 pH units, decreases the concentration of hydrogen ions by 37%. So do you think the bacteria feel that? Yes, they do. So it's important. pH is a particularly important variable for maintaining control. All right? So E. coli, now the good news, that's the bad news. The good news is that the bacteria have little hydrogen pumps in their internal, at their interfaces. So if you put them in a too high of a pH, that's going to be like a basic system, and so they can adjust their hydrogen, they can adjust their internal pH by using their little hydrogen ion pumps. So they will maintain their pH at about 7.6 regardless of what you grow them in, okay? And so, but they will grow best under a certain pH, which is typically around 7, all right? So just because they maintain their internal pH at 7.6 doesn't necessarily mean that that's the best pH for growing in. All right, so the operation of those little ion pumps requires energy input. So this is part of the maintenance cost, that the bugs consume some glucose and they maintain their hydrogen pumps. So, so bugs tend to grow more slowly when the pH is not at the optimal pH. So this is an important variable. And so now how do we control it? We've got a pH probe. Everyone's familiar with this. pH probe, pH monitor, and it's really a controller. And I noticed this time I drew a little line from the controller to the pump. And we also are going to have an acid pump, because if the pH goes up, then we want to pump in acid and bring it back down. If the pH goes down, we want to pump in base and bring it back up. So we want to have both pumps under an unknown circumstance, but I can assure you that for our bug, really it only produces a significant amount of acids under normal, healthy conditions. So we really can get away with just having the base pump. We never have to worry about it going up. And if it does go up, it's